Okay, I thought I'd give you one more quick example where we didn't just have one rational zero. So I chose k of x. K of x is kind of unique. If you look at the graph, you do your p over q, you're going to actually find that there are two actual rational zeros in that list. Specifically by doing trace on your calculator and seeing that's a little over 2, and out of my list, 11 fifths is 2 1/5. That seems like a reasonable value. I look at that, I fill it into my table, and it indeed gives me 0. Similarly, looking at my list and looking at the graph, it looks like -1/3 is a 0. I fill it in the calculator, and indeed by doing trace and then typing in my x value of -1/3, I get 0 as a result. Okay, so that lets me know that we have two rational zeros. So it's kind of unique. What I did next then is, unlike the one in class, I did a running division. Okay, so by choosing one of those to start with, and honestly it doesn't matter which one, so I just started with -1/3, I divided synthetic division. It started out, remember, 15x to the 4th. Okay, I divided out a single x. That brings me down to an x cubed, so that's -15x cubed plus 33x minus 135, or excuse me, 33x squared minus 135x plus 297. X cubed I can't do anything with. So then I decided I'm going to factor out or divide out one more x value, 11 fifths, which I knew from up above was an actual rational zero. So I'm dividing kind of like I would take a number like 12 and I divide it by 2 to get 6, and then I'd take 6 and divide it by 2 to get 3. 2 times 2 times 3 would be my factorization. So using that same principle, I'm going to take my leftover, which is 15x squared plus 0x minus 135, or just 15x squared minus 135. I could use quadratic formula with these as a, b, and c, but in this case, since I don't have an x value, I'm going to go ahead and simply slide the 135 over, divide by -15, and then take the positive negative square root, and I get 3 and -3i. That lets me know why I only saw 2 zeros on my graph. Both appear to be multiplicity 1. Well, it's because the other 2 were imaginary. So I had an x to the 4th. An x to the 4th should yield 4 zeros, and this, or some repeated zeros with multiplicity. I indeed have 1, 2, 3, 4 zeros, 2 of them real, 2 of them imaginary or complex. Okay. I then turn those into factors. The first one I multiply both sides by 3 to make that 3x equal -1, and then I shifted the -1 over to make 3x plus 1. Similarly, I came up with 5x minus 11 for that factor. If x equals 3i, then x minus 3i, by moving that to the other side, gives you by setting it equal to 0, gives you the factor. Okay, and then similarly shift that the other side and I get x plus 3i. So there is my linear factorization of the original function, -15x to the 4th, blah, blah, blah. Okay, so that gives you kind of an extra example, a quick one, a variation to the one we did in class.